Thank you. Good evening. My name's Alf Kuchenbuch, and I work for Brainchip, and I'm doing the sales activities in Europe for Brainchip, together with my colleague Gilles Bézat from the Toulouse office. Uh, yeah, today I think we have a quite interesting topic. It's all about space. It's all about rockets, and it's about AI going to space. I'll be talking about a couple of things today. First one is that the space community, like European Space Agency, but also NASA or Australian Space Agency, are picking up now on AI. They want to have AI in space, um, and they are conservative. So of course they are a little bit reluctant with risk averse, but they do see the necessity really hard now. So they're picking up with a certain urgency right now. Next point is I will tell you why AI and why specific neuromorphic AI is so necessary in space, and what kind of use cases are there that can only be handled by AI, basically. And then I will be telling you a little bit about our solution for the neuromorphic processing. And then I will go go on and show you a little bit about our cooperation with a big space chip maker who wants to integrate our Akida chip into their next system on chip, space SoC, which is radiation hardened, and that making it fit for these missions like landing on the Mars, for example. Then we will go on by looking a little bit into the future, what's coming, what kind of extra features will come in the future for neuromorphic processing. Good. So this was a workshop we attended 2 weeks ago. It was from the European Space Agency. They had 80 people there. Those were hardware manufacturers, semiconductor manufacturers, but also the sub-suppliers for the European Space Agency, like the Airbus and Thales Alenia Space, whoever is there, and all the experts from the universities as well, and so academia, and the manufacturers for the software ecosystem for neuromorphic processing, basically. And they brought them all together 2 weeks ago. And so there was a lot of discussion going on. And nice thing is everybody was able to pick up the point of view from everybody else. And this way learning about what is really necessary for AI in space. And one of the big outcomes was basically that anything that's happening on the Earth right now will be or is expected to be happening in space 5 years later. So when we're talking about data centers with so many gigaflops happening right now on the Earth, this is something that 5 years from now we can actually expect in space. So that was something that was kind of shocking for some. But also something which is probably an inevitable truth. So this will happen. Things will evolve. Yeah. So yes, European Space Agency has picked up on it. They have even put up or they've done an active first step by bringing together all these experts. But also NASA is picking up on this, and this is sorry. This is a LinkedIn post, and I kind of like that because yeah, even NASA is posting their stuff on LinkedIn. So I think it's kind of cool. And it's from Dan Golden, and he was the NASA administrator in the 90s. And he picked up on there's basically no way we need AI in space. What he says here is most of the time the data that's picked up by the satellites right now, which could be camera-based images, could be some kind of other signals. They would be taken by the satellites and then sent down to Earth, which makes the sensor a dumb sensor in a way. Just pick up the signal, send it down to Earth, and then do all the intelligence on Earth, which, sorry, which is easier in the way of that you don't have to bring AI or data centers into space now, but you can do everything on Earth and you have time for doing that. But the disadvantage of that obviously is that that you need to transport a lot of data, and thank you, but the data links are yeah. There's only so much capacity you have on the bandwidth side that you can beam down for data. What it says down here, I'm not 100% on his side here, because I think what he says, it all comes down to the semiconductors, but the semiconductors alone, I'm not so sure. I think it's the whole ecosystem. It's like with a PC. If you have a fantastic PC and you don't have the software running on it, what's it for? So I think you need to have like the whole package. So I think just looking at the semiconductors here is just a little short. But yeah, we will see a little later here. Good. So also, like, European Space Agency is on track, NASA is on track as well. So why do we need AI in space at all? It's basically two reasons here. It's the first one up here. First one is latency. So if you imagine that you have like two satellites and they need to go docking, then first idea might be, okay, I'll do, like, can be a human controller and he sits there with a remote control and steers them until they dock. You can do that if it's close enough. It's like low Earth orbit, for example, you can do that. But as soon as you go further away, then the signal, like the camera signal, for example, that needs to go down to the operator, needs to travel a very long distance. And then even with speed of light, we're talking about a lot of latency here. So that by the time you have steered it to this way, then you probably already need to go to the other way again. So that's not really possible. And that's why autonomy is so necessary. So the satellite needs to know by itself what to do, and then take the right action. So the first one. The other one is you don't have that much bandwidth for transmitting from the satellite down to Earth, because there is like the satellites, especially in low Earth orbit, they're moving around the Earth, so they have to jump from one to the next ground station to transmit their data. And then there's so many satellites up there, especially with the new constellations, like Elon Musk's satellites. All of that, it's getting like more and more and more. So there's a few ground stations and they need to be shared by so many satellites. So that means you cannot send everything down to Earth, but there needs to be intelligence happening in space itself, so that you can compress the data rate, the amount of data. You can do that for example, by looking at, yeah, we'll get to that a little later. But getting the amount of data compressed and then just have to send down less information, or at a higher, like at a meta level, basically. So let's look into the use cases here. First one is Earth observation. So that's all the satellites going in low Earth orbit around the Earth, taking pictures. Many of these pictures are clouded, so that they're just looking at white stuff, and there's like, you cannot see anything from what you want to see at the Earth. Those pictures you can do some kind of semantic segmentation. So you pick out, okay, here is clouds, and then you just cut it away, and then you only transmit back to the Earth whatever is left, whatever is valuable data. You only send that down, and you could also compress that losslessly. And then you already bring down the required bandwidth quite a bit. But there's another thing also, like the wildfires and ships. Here you can even compress the data much more down just by looking at you just pick up or the satellite just picks up where the ships are on the coordinates and just sends down the coordinates. It doesn't even need to send like the picture anymore. If something's interesting, then it still can send the picture, but as long as it's just plain water, you don't send anything. So that will be like for Earth observation. For planetary landers, we'll get to the case a little later. I will show you just a little video what a lander sees when it's going down onto the lunar surface. Yeah, and then it needs to detect like what Neil Armstrong did during his own landing. He saw a lot of rocks, bigger rocks, and he didn't want to land in these rocks, so he was doing manual override and moving away from these rocks. That's also what the artificial intelligence could be doing for in this case. So that's that. Rover and drone navigation. Let me just show it real quick. That would be like a Mars rover here. That's Rosalind Franklin. That's from the European Space Agency. That's the next one that's going to Mars from our side. And drones here, like is it Ingenuity? I think it's Ingenuity from NASA. They also need a lot of more autonomy, which they can get by finding rocks that are too high to climb, for example, or maybe some drop off, which they should detect by themselves, so that nothing goes wrong here. And then there's autonomous docking. I was talking about that. If like two spaceships are docking, they would also need to be way more autonomous than they are right now. And then there's next one here, debris removal. Yeah, there's so much space junk in space right now that there are plans to remove this by just picking it up and slowing it down and then having it burn, all these things. And then space situational awareness, meaning some debris that is maybe not expected, that's coming too close to your satellite, and then you can do evasive actions, anything like that. But also bringing back this whole topic of autonomy. So that's why AI in space is so necessary. Yeah, here are the different use cases. Here, the docking scenario up here, the rover, the drone, the lander here, Earth observation, and here like fixing satellites, repairing, doing something in orbit, and also debris removal. So that's the reason why we need AI in space. But why do we need neuromorphic AI in space? Neuromorphic AI has a big advantage over conventional AI, and that is that it works in the principles of the brain. So what that means is in the neuromorphic or in the event-based domain, what's happening is the processor only does processing if something happens, if an event comes up. If no changes appear, the chip will not do anything. It will only do something if it's triggered by an event. And that brings down the power demand so much that it is orders of magnitude better. So there's lots of applications which you have like with the constrained power availability on the satellite. You can only do if you bring down the required power. Yes, and as I said, if nothing changes, that means that the input data is sparse. So you have lots of zeros in there, and then you don't have to do any calculations at all. It's not even that you calculate or that you multiply by zero, but you don't even touch that. It's just like the brain works. don't do anything unless you have to do something. And the disadvantage of some of the neuromorphic approaches is that you only can run spiking neural networks, but this can be overcome by having like a converter basically that converts CNNs into SNNs, and that would be something that we have invented as well, and it is available. So on the Akida processor, you can run both CNNs and spiking neural networks, both. Okay, so here I want to tell you a little bit more about this thing about sparse or event-based action by only looking at the data that really changes. So what you have here as a scenario is what a lander sees when it's going down on the lunar surface. And in this way, it's going up and down and up and down. But anyway, what you can see here, this is the picture from a normal camera. What you see here, that's an event-based camera. And this only shows in red and green. It only shows something that changes from one frame to the next one. And all these changes, that's basically that's a dangerous point, and that's necessary for the lander to know, because you wouldn't want to land on anything like that. For the processing side, everything that's red and blue needed to be calculated. Whatever is white here is not even touched. It's not even calculated. It's just blanked out, and that makes it so power efficient. Okay, right. And then there's one thing. If I stand in front of the of such an event-based camera, and I don't move at all, then the camera doesn't see me anymore. So there's in some situations, and I get the question quite a lot. It's like, okay, but then the camera doesn't see you anymore, or it doesn't see something else anymore. So it's dangerous, right? And it's not really dangerous, because the camera doesn't see you, but the model that's doing the inference, that still remembers you, because you stepped into the picture, and then you are there, and then all of a sudden you disappeared. And the model knows that it cannot happen that something just disappears or something. And that way the model remembers, okay, so he was here, I cannot see him anymore, so he must be standing still. So this information is not really being lost. Okay, so now let's look into, yes, how is the Akida chip made so that it is it can be so fast and so power efficient. What we do is we have these small computers basically here. Those are 4 neural processing units, and they share a piece of memory. And we have these things 16 times side by side, 20 times side by side. So you have many autonomous little calculation units, and they only require the data that's inside their own memory. So there is hardly any need for getting something from the system memory. So then they would need to share one big data bus and to get the information, but not in this case, because most of, or 99% of all the information is already stored here in their own local memory. And that makes it overcome this bottleneck, the von Neumann bottleneck, and that way it can be so quick and also power efficient, because you don't need to do all the transfers with the main memory. Okay. Yes, and what you do is when you load the model into this, we call it mesh, all these many nodes side by side. Once you load the model into the mesh, you do this once, and then you put the weights into this memory here in each one of them. And then the next thing that's happening is you take the picture, that you want to do the inference on, and also put it into these, like you cut it up into pieces, and then you put it also into these memories. And then these little units can work autonomously all by themselves. And then once they've done their stuff, they return the information back to the host processor, and the host processor can then do something like post-processing and then give an output. Say, okay, like here's the crater, maybe move a little bit over here. So that's how Akida works. And that's why I was not so happy about the statement that it's only the semiconductor that's important. But what it needs is here's the Akida processor, but to feed the Akida processor, you need to have a trained model. And what we do have here is we come from TensorFlow Keras over here. So it's like a standard environment with which you work, or the workflow. And then what you do is you put it through this CNN to SNN here. That's a part of our own development environment that translates basically the Keras TensorFlow world into the Akida world. Once you've done that, you can download it onto the processor, and then this thing does its thing automatically and autonomously. And as I said here, you can take either a pre-trained model from our zoo, then we have done the work for you already, or the other thing is you can train it a model all new in TensorFlow. So there's many opportunities here of getting the right results. Okay. Oh yeah, and you can download the Akida, the MetaTF environment for free. You can download it just from the internet, and then you can simulate the Akida chip, and so that way you can get your hands dirty and can get first experiences with what Akida can do, because the simulator is included into that as well. And yeah, and then the second step would be buying one of these boards here, and then trying it out in the real world. Okay, so now we were talking a lot about how should it look like, what can come in the future. Now we're getting to reality. So Akida is in space right now. In March, this Falcon 9 rocket started with a Transporter 10 mission, and it has a little computer on board, which I can show you here. That's the little computer. It's like this big. It's called the brain, and it has Akida inside here. That's our chip, and it's in low Earth orbit at the moment. And we're waiting for the first moment when they switch it on and let it do its work. It is doing some kind of image classification. They couldn't tell me more what it is. It's all very secret. Yeah, so that was launched in March. And then we have another project here with our friends. Oh, no, I have to say the word. This is N61. It's an Australian company, and they're not really big, but right now they're getting a lot of attention for being the first ones bringing neuromorphic AI into space. Another one is EdgeX. They're Belgium-based, and they also make processing stacks for space, for controlling little satellites. And here you can also see the Akida chip. This one is supposed to be launched into a CubeSat, like one of these small satellites here. And this is supposed to do all the control and be the brain for the whole satellite. Right. Yes. So what I was talking on this slide is commercial, or they call it new space. So everything that goes around the Earth, which is, well, it's not a catastrophe if one of these things doesn't work. then you just replace it with something else. So it's more like the commercial side of space applications. So we call it class 4 and 5 here. And now we're talking about the real deal, and that is the space. That's the space missions which cannot go wrong at all, because it's multi-millions or multi-billions of dollars involved here. That's what they call the class 1 to 3 space missions. And for here, you need that's mostly for missions that go further, like into deep space, where you have a lot of radiation, where you have many other things that may give your components a hard time. So for that, it needs space grade processors, and these space grade processors are radiation hardened. They're fault tolerant, and they are made by only a handful of manufacturers. One of them is Front Grade Geisler, and they are based in Sweden. And they make the next generation. They're only just completing the next generation space grade processor, and we're in very close cooperation with them to integrate Akida into their chip. And that would make us really, really proud if that works out, because then we would be scheduled to go for the moon landing or even for Mars. Looks good. Let's keep our fingers crossed. So what's next? That's basically my last slide here. What's next is we're looking into the second generation of Akida. And what this can do is it brings in a new model, which is called TENS. We call it TENS. And that is, I can see it. Yeah, it's a spatio-temporal convolution. Sounds very difficult. It's not difficult. What it is you have a two-dimensional image, basically, just like the picture. And what we add to it is the third dimension, which is time. And that's very necessary for these scenarios we saw earlier with the lander that was landing on the moon, because then you have not only the picture itself, but in the first frame, it's up here, and then it's getting closer. So you have this temporal aspect inside your convolutions now. What it does is it makes video and audio applications much faster, very efficient, reduces the model size, which is good because smaller size is definitely more power efficient, and it replaces the LSTM models that are used currently, and the GRU models as well, because it can cover all this functionality. When you come to our booth, which is over there with Edge Impulse, we can show you more about that, and we can also talk about this new future technology with TENS, and then we can look into that, and we'll explain a little bit more. But for the sake of time, let me just go through the summary real quick. 3 points I'd like you to keep in mind is that neuromorphic processing is super efficient, and with that, second point is basically you're using a standard tool chain for doing the programming or the model building for putting it onto Akida. And the third one basically is Akida is not a dream. Akida is there today. It's up there today, and it can be used. And just let's talk about how we can implement it into your application. Would be fantastic. Our booth right over there with Edge Impulse. Thank you so much.